Hello, I am Kevin Mato, a former master student of the Polytechnic of Milan and a PhD student at the Technical University of Munich. So, today we will talk about molecular unfolding with quantum annealing. The in silico approach to drug discovery is a multi-tiered process that encompasses several computational techniques with the objective of screening databases of the order of billions of molecules to forward to the later experimental stages. One of the techniques involved is molecular docking that simulates on atomic level the interaction between a compound, the ligand, inside the protein's binding site called pocket, in order to calculate the preferred position and shape of one molecule to a second one when bound to each other. When each molecule is evaluated on pharmacophoric features, we have an extreme computational cost, and that's why we are using geometrical approaches that unfortunately have some biases. One of the biases in our case is a shape bias that is induced by the tool SMILE to 3D, that is taking the SMILE representation and translating it in a 3D representation of the molecule. That is useless because it's created and in a disconnected fashion from any type of criteria. The initial shape impacts the final docking quality, and the removal takes as much as the docking itself, and that's why we need a whole initial phase called the ligand expansion. That is a technique that we use to remove the initial shape bias. Okay, so let's start with an interpretation of the molecule. That is a flexible set of atoms connected by edges or bonds at a fixed length, where two consecutive bonds are set at a predetermined angle. A subset of these rotatable bonds, is called rotatable bonds, that when virtually removed, they are defining two non-empty disjointed fragments of the molecule. Each fragment can rotate by a discrete angle, and we assigned a variable theta I to this angle. And the set of the assignments of these variables theta I will be called the conformation of the molecule. So our objective, in order to remove the shape bias, is to find the unfolded torsion configuration that maximizes the molecular volume, or equivalently, that maximizes the distances between fragments. Okay, mathematically, how do we define a rotation? We use rotation matrices that are a function of the theta angle of each rotatable bond. And in case we will have multiple rotatable bonds in the path from an atom Ca to an atom A0, the operation of rotation will be the application in sequence of the single rotation matrices. Okay, on the left-hand side, you can see two of the features representing the molecules in the database of our project. And we are representing the number of atoms and the number of fragments. The number of the most widespread molecules are the ones with 40 to 50 atoms and 10 to 20 fragments. The number of fragments is useful because usually the number of rotatable bonds is upper bounded by the number of fragments divided by 2. And this information is very useful because it can tell us how powerful is our method and how many molecules we can actually solve in our database. On the right-hand side, you can also see that these two features are a proxy for the volume because there are 118 molecules ordered in increasing volume, and we can see a positive correlation between the number of atoms and number of fragments with the volume. Okay, let's literally divide now our molecule into fragments. First, we have to iteratively pick out the rotatable bonds that are the dimensions of the shape space. And then we have to define the between centrality in our molecule. And this attribute allows us to define an ordering by centrality of the atoms inside the molecules graph. Then we enrich the definition of fragment as the set of atoms that share the same rotatables influence set, or the rotatables that influence the same set of atoms. And we calculate it as the intersection of the rotatable bonds with the bonds on the shortest path from the atom AK to the central atom. Okay, now we will see two of the alternative algorithms that we use to compare to quantum annealing. And the first one is random search, that belongs to the family of probabilistic algorithms, usually used in hyperparameter optimization in machine learning. And in this case, we are picking out candidate combinations from a random uniform distribution, and we are evaluating them in the function that we want to optimize. And in our case, we implemented it with several processes running in an embarrassingly parallel mode, where each process is picking out randomly candidate optimal solutions, optimums from the subspaces that we found as subdomains with the same number of dimensions as the initial shape space. Then the second algorithm is GeoDoc, which is a greedy algorithm, and this is inspired from the original version of the ligand expansion. This algorithm gives us approximation of the optimal solution in a reasonable time, and we have implemented two variants of this one. The first variant is the GeoDoc, original GeoDoc, where we are trying all the possible combinations for the first rotatable bond, and then we're finding the optimal angle for the first rotatable bond, and then we proceed to the second one, the third one, and the fourth one. Or we can do that in a batch mode, where we are trying to find the best combination for the first two rotatable bonds, and then the second two, and then three, and then one. And in our implementation, we tried the combination for 4 rotatable bonds at a time. Okay, so what does it mean to find the unfolded torsion configuration in a mathematical way? So it means that we need to find the set of assignments of the angles theta 1 to theta m that maximizes the sum of the distances AB between fragments A and B inside the molecule. So the total distance will be the sum of these distances between fragments A and B squared, where the distance A and B squared is the squared modulus of a fragment A in initial position minus the rotated position of the fragment B. Okay, so how do we achieve our formulation? Is by considering a discretization of the torsional angles theta I into d possible values, and then we perform a one-hot encoding by introducing a binary variable xik with k between 1 and d, such that xik is 1 if the theta I rotation is equal to theta ik or 0 otherwise. And since it's a one-hot encoding, we need a hard constraint that only one of these binary variables will be equal to 1 for a certain torsional. With such encoding, the rotation matrix will not be a function of the angles anymore, but a function of the Boolean variables. Okay, since we can't usually get a Kubo formulation straight away, we start from the construction of the higher order unconstrained binary optimization problem. And the formulation will be like the one in the box, where the first term is the hard constraint multiplied by a constant that modulates its strength, minus the optimization term, minus because we want to maximize this function, while the overall optimization formulation will be minimized. In general, if the distance between two fragments A and B depends on m torsionals, the highest order in the Hubo will be 2m. Thank you, and now I will let my colleague Ricardo that will explain you our results.
Okay, thank you. Thank you, Kevin. So my name is Riccardo Mengoni, and I work at Cineca. I'm a researcher at the Quantum Computing Lab at Cineca, which is the Italian supercomputing center. Okay, let's go on with our presentation. Okay, and let's talk about the Hubo problem structure. Let's say that in order to obtain a precision of delta theta I in the granularity or in the discretization of our torsional angles, we need the number of variables for each torsion, which is d, which is equal to 2 pi over the discretization. Given a molecule with m torsions in general, this means that we need a number of variables which grows linearly with the number of torsions. It's d times m. In our study, in our experiment, we use molecules. We study molecules ranging from 20 to 50 atoms and up to 10 torsions. For these molecules, we selected a precision or a discretization of the angle equal to pi over 4, which means 45 degrees. The reason behind this choice is explained in this slide. So on the plot on the left, you see that the degradation due to different granularities is actually always very low. And in particular, if you go from a discretization of 1 degree to a discretization of 45 degrees, you are left, the degradation that you get is always below the 2% and goes to 4% only for very large molecules. And actually, if you look on the plot on the right, on average, we got a volume gain of 70% using the 45-degree granularity versus the situation where you do not consider the unfolded configuration, but an initial folded random configuration of the ends. Okay. Let's now have a look at the linear and higher order terms that appear in the Hubo when the granularity, when the discretization is pi over 4. You can see on the left the histogram about the linear terms, which, as we've seen before, grow linearly with m. So we have 16 linear terms when 2 torsions are considered, up to 64 when we have 8 torsions. For what concerns the higher order terms on the right, this is log scale, and the higher terms increase exponentially. So that's why we use different colors, which means that we had to introduce an approximation in order to treat the problem correctly and to address the problem using a D-wave. So basically, our approximation works in this way. We deleted the Hubo terms that were below a certain threshold. And this was applied in 2 phases and helped us to speed up the construction of the Hubo in the first place, but also to speed up the transformation of Hubo into Cubos, so the quadratization part. And moreover, this approximation enabled us to solve the problem, the Hubo problems, natively on the D-Wave 2000 and Advantage. Here you see the linear and quadratic terms after the quadratization. As you can see, columns in the histograms with the same color are associated with the same threshold value for the approximation, and columns belonging to the same section are associated with the same number of torsions. As you can see, usually increasing the number of torsion while keeping the threshold fixed, you have an increase in both in the linear terms and quadratic terms. The opposite happens when you fix the number of torsion and you increase the value of the threshold, because in this case, the columns decrease in value. So you reduce the number of linear terms and the number of quadratic terms in the Cubos. The only strange things happen when you have 8 torsions, where basically the orange column is shorter than the green one, and that's just because with that level of threshold. The orange one is a threshold value of 100, which was too low in order to embed things correctly on the D-Wave. So that's why there is this little bias in the 8 torsion case. However, we were able to embed all of our problems in the D-Wave architecture, both on the D-Wave and D-Wave 2000 and Advantage. We've seen, in general, an improvement for what concern number of physical qubits used and shorter physical chains of physical qubits that are used to encode a single logical variable or single logical qubit. Okay, on average, both are around 50%. There is a 50% gain in both of them. Okay, let's now talk about the first result that you can see here. Here we plot the volume gain in time expressed, absolute time expressed in seconds. Okay, here we have 4 torsions, and as you can see, we plotted the result obtained with the QUBO solvers, which are simulated annealing, Advantage, and 2000Q, but also the classical solver that do not solve the QUBO problem, which are the random search and Geodoc that Kevin explained. As you can see here, simulated annealing works very well. Under 5 seconds is able to reach a good solution. Also, random search works well in this case. Advantage, however, after 20 seconds is able to provide the best solution overall. Things start to change when we go to 6 torsions, where Advantage and 2000Q start to suffer the fact that the dimensionality of the problem increases a lot. For what concerns simulated and random search are a little bit better. Simulated actually is very stable. In fact, if we look at the problem with 8 torsions, again, simulated annealing is absolutely stable, and Advantage and 2000Q have need more computational time. But it is something that we expected because these are physical devices and they need programming time or sampling time, which is not present in the simulated annealers or the other classical techniques. Okay, so this leads us to the next slide, which is this one. So basically, when you compare performances of annealers, simulated annealers and quantum annealers, talking about absolute times in seconds is not very helpful, okay, because these are physical devices that have this kind of limitation right now. So what we plotted here is the time to solution, which is the total execution time divided by the number of currents of the best solution. Here, which basically is telling us a probability of finding the optimal solution in a unit time. Here, the lower the better, so simulated annealing works well, but Advantage is very close because this is log scale, and for sure Advantage outperforms significantly 2000Q. Same thing happens for the volume gain, plotted increasing the number of torsions, where Advantage works well, but for small problem sizes. Finally, we have the volume gain over TTS, which is normalized in order to have all the 3 methods on the same scale. So this we came up with this metric because we wanted something that was able to take into account both the quality of solution and the time to solution. And basically, this measures how fast the method fails to provide a good solution. And the important thing here is the slope. And you can see that Advantage has better slope than the 2000Q, but also of a better slope with respect to the simulated annealing, which was the best one. Okay, so in conclusion, basically we tackled the problem of molecular unfolding, which Kevin explained. We gave a Hugo formulation of the problem, which can be solved with a D-Wave annealer. Finally, then we also had to introduce some approximation in order to decrease the problem size and embed the problem on the D-Wave annealers. Advantage and 2000Q were different in performances, and for what concerns the bending, Advantage was basically 51% better for what concern physical qubit and chains. In terms of absolute time, simulated annealing was the fastest method. But if you look at time to solution and volume gain, but also the new metric, normalized volume gain over TTS, Advantage show a significant improvement with respect to 2000Q, but also a promising result, also considering with respect to simulated annealing, also considering that future generation of quantum devices can increase the sampling technique or also reduce the computational time. Okay, so I'm going to leave you with the last slide where you can find the reference, our contact, and so thank you for listening to our presentation. So feel free to contact us if you need further information or question. Thank you.